So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione. I'm the interim director of NITheCS at the moment. And today I have the very big pleasure to introduce to you Professor Frans Pretorius. Frans is a professor of physics at the Princeton University. And he was very modest in the bio that he shared with us. But I know that last year he won the very prestigious Dirac medal from the ICTP. And so congratulations for that, Frans, from all of us. Yeah, so thank you very much. And I think he also won many other prizes. If you go on his Wikipedia page, there is the whole list. But what is probably, most of you probably know, is that in 2017, he won another very prestigious prize, the New Horizons in Physics prize, for his fantastic work in, let's call it, computational physics. He was the first one to simulate the fusion of two black holes on a computer. So that's probably was a very historical simulation. And today he agreed to give us a talk from Princeton, and that's why we shifted our initial time by an hour because he's in another time zone, and he give us a status report on gravitational waves astrophysics. So Frans, thank you so much from all of us for your time, and we are really looking forward to what is probably a very interesting talk. Thank you very much.
Well, thank you very much, Francesco. Thank you for the invitation. It's a pleasure to give this talk. Thank you for the very kind introduction. So let me now just share my screen. Let's see, okay. Okay, so can everyone see the PowerPoint?
Yes, it's clear and perfect. Thank you very much.
Okay, and can people see my mouse pointer?
Yes, we can see that as well. Thank you very much.
Okay, great. Yeah. Okay. So yeah. So what I'm going to give is a status report on gravitational wave astrophysics. So here's kind of the outline of my talk, or the first part of it. So from my perspective, one of the most profound and interesting things that's come about in the last few years by the gravitational wave observation of the universe is that we can understand the dynamical strong field regime of Einstein's theory of general relativity. And so since most of the talk I'm going to be focused on that, I thought I'd give an overview of some of the basic properties of strong field gravity, gravitational waves, and how they're produced, so that we're kind of all on the same page. And then when I describe what I think is so profound about what's been discovered in the last few years, or what we've been able to test about strong field gravity, hopefully you'll be able to appreciate that. So I know probably not everyone here is very familiar with general relativity, so there will be some equations, and don't worry too much about it. I'll try to explain them at least in words. But even if not, don't worry, we'll get to perhaps some of the more sort of interesting stuff later on. So then I sort of decided to pick kind of three highlights from the LIGO and Virgo detections of gravitational waves over the last few years that I think, at least in my opinion, are some of the most interesting. And it's this first one, to give the first quantifiable evidence for the existence and dynamics of black holes as governed by general relativity. I'll spend most of the talk motivating that and discussing that. And some of the other two topics, sort of all the very interesting things that were discovered by the first observation of a binary neutron star merger. A whole talk could be spent on all of that interesting information, and just for time constraints, I'll just very, very quickly go over that. So I won't say much about that, but that was a really astonishing discovery. And then I'll finish with giving some hints that the population of stellar mass black holes in our universe might be a little bit unusual, kind of unexpected. Okay, so again, this is all from within the context of Einstein's theory of general relativity. And what Einstein's theory is, it's a theory about the structure of space and time, or space-time. And it posits that we can describe space-time by a four-dimensional geometry. And perhaps the most convenient way, or one convenient way to describe this geometry is through the so-called line element that I've written out here. And it's, if you will, it's just an infinitesimal version of Pythagoras' theorem, saying that the infinitesimal distance squared along some direction is this sum of distance squareds along the individual directions. And this is what I'll be using throughout this talk, is the so-called Einstein summation convention, where we just dispose of the summation sign. So this is exactly equal to that, where the sum is implied over where indices are the same. But just think of this, you don't worry too much about this if you haven't seen tensor expressions. Just think of it as a version of Pythagoras' theorem. So we're interested in distances between 2 points or between 2 time intervals. And all of the interesting geometry in space-time is characterized by this metric tensor, this G underscore A sub B. So to understand the geometry of some particular scenario of the universe, we want to know what the metric tensor is of that particular situation. So Einstein's theory, it's okay, that's one crucial thing. It says that space and time is this geometric object. But the other thing, perhaps the most challenging thing about general relativity, is it's not just that any old particular geometry works, but the geometry must satisfy the so-called Einstein field equations. And that's what I've written here in tensor form. So on the left is something called the Einstein tensor, which characterizes curvature in space-time. And on the right-hand side is the matter and energy in the space-time, like the Earth, for instance, this TAB. And here I'm putting this is Newton's constant, this capital G, and C is the speed of light. So it's G over C to the fourth is this dimensionful constant that multiplies the right-hand side. Now, I mentioned before, if we want to understand something about the geometry of space-time, we need to know what the metric tensor is, not the Einstein tensor. But it's written in a deceptively simple form here, but if we expand out the Einstein tensor in terms of the metric tensor, it turns out to be a set of 10 second order coupled partial differential equations acting on the metric tensor. So that's what we have to solve if we want to understand a metric for a particular situation. So what are some of the solutions? Well, one of the very simple solutions is if we say, well, let's look at a vacuum space-time. Let's set the stress energy tensor to 0. And one solution is the geometry of special relativity, so-called Minkowski space-time. So this is the line element here for Minkowski space-time. Again, so think of this as sort of Pythagoras' theorem. You can see the Euclidean part, x squared plus y squared plus z squared. But then time comes in, and the interesting thing is that time comes in with a minus sign. Okay, so this is the metric element for Minkowski space-time. But sort of the main thing that that's new that's coming out of the LIGO observations is we're going very far from the space-time of special relativity. We're going to strong field sources. And one of the interesting things about Einstein's theory is, even in vacuum, so you still keep TAB equal to 0, this Minkowski space-time isn't the only solution. And that's because the Einstein equations are nonlinear. So there actually are different solutions that all satisfy the vacuum equations. And a couple of the non-trivial vacuum solutions that are allowed are black holes and gravitational waves. So they're going to feature prominently here. So let me describe that in a little bit more detail. So first, let me focus on so-called weak field gravity, where the geometry is Minkowski space-time plus a small little perturbation. And in the weak field setting, it's kind of easier to describe in a concrete sense what gravitational waves are. I mean, what some of the predictions of relativity are. So gravitational waves, if you want to think of pictorially what they are, these localized disturbances or sort of ripples in geometry that propagate at the speed of light. So they satisfy the Einstein equation. So we want to think here of that the actual metric here is the Minkowski metric, this eta AB that I wrote here, plus this HAB, which represents a small perturbation. And so if we take that, we plug it into the Einstein equations and we solve it to linear order, and we ask, well, what does it tell us? What are allowed for propagating degrees of freedom? We find that the Einstein equations allow two linearly independent polarizations. One's called the plus, one's called the cross. And here, without loss of generality, let's just consider a wave that's propagating in the z direction. And the solution can be written as a sum of this plus polarized wave and this cross polarized wave, where here this h plus is an arbitrary function of t minus z over c, and h cross is an arbitrary function of t minus z over c. So we can see that the waves propagate at the speed of light in the z direction. But the interesting thing is that these polarizations only affect geometry in the direction that's orthogonal to the direction of propagation. So here in the xy direction. So perhaps I can sort of visualize this. This might be easier. So let's imagine kind of a sinusoidal disturbance in geometry that's propagating in the z direction here, what I've sort of illustrated here on this in between. So this is this perturbation in the geometry that propagates in the speed of light. So this is a perturbation away from Minkowski spacetime. And so it tells you how distances are stretched and squeezed. So if you imagine you're just starting with this ring of particles, just sitting, there's no gravitational wave, it's just flat empty space. And you ask, well, what does it mean when a gravitational wave passes? And in this case, into the slide. So it's going into the z direction. X and y is on the plane of the slide. And for the plus polarized wave, as you can see, sort of as it passes in with time here, it first stretches the wave in the y direction, then it goes back to, sorry, the space-time in the y direction, then it goes back to a circle, then it stretches it in the x direction. So there's oscillatory stretching and squeezing of space-time as the wave passes. So that's what a plus polarized wave does. The cross polarized wave illustrated below is qualitatively the same, except it's rotated by 45 degrees. So what linearized Einstein gravity tells us is that for these weak field disturbances, in general, in one direction, there can be some arbitrary superposition of these two kinds of distortions of space-time as the wave propagates. Now, one thing that's going to sort of feature prominently, well, that's sort of very interesting about the sources of gravitational waves that we get to is, one question is, well, how much energy does a gravitational wave carry? And that is that's given by this expression. So this is the energy flux in a transverse area A in an amount of time dt. And it's given by the sum of the time derivative squared of the plus and the cross polarizations. So very similar to electromagnetism, if you want to think of it in that way. So this dot here is a time derivative. So it's a sum of h dot squared plus h cross dot squared, sorry, h plus dot squared plus h cross dot squared. And these angle brackets mean a time average. So that's just a technical thing in relativity, in that it's impossible to localize gravitational waves. So we have to average it over a characteristic scale of the wave. But just think of this sort of the sum of the time derivative squareds. But then the one thing that's perhaps very interesting about this expression is this dimensional constant that multiplies this right-hand side. So it's c to the c cubed over Newton's constant. And this evaluates to 10 to the 35 joule seconds per meter squared. So what that tells you is, so these are the right-hand side here with the h's are changes in geometry. So we think, if a gravitational wave passes us, we should be able to see, space-time distorting. But this incredibly huge factor tells us that if we want to see, some kind of a noticeable amount of distortion in space-time, the energy that it would have to carry for us to notice it easily is tremendous, like almost astronomical. And that's why we have to look to astronomical sources. So space-time is incredibly stiff. It requires a huge amount of energy to distort it even by a small amount. And that's why, you can think of gravitational waves very much like electromagnetic waves, but it's completely impractical to build like receivers and transmitters on Earth to study it, just because of this huge factor over here. The amount of energy that it would create is just impossible to achieve on a lab on Earth. So that's why we have to sort of look to sources in the universe, such as black hole collisions, which I'll get to later. Okay, so about sources. So how do you produce gravitational waves? And here we can also appeal to linearized gravity, the so-called weak field. and get to the famous quadrupole formula. So what produces gravitational waves is an asymmetric acceleration of energy. So the energy can actually be in matter, stuff that you can hold, but because of E equals mc squared, it's equivalently energy. So any kind of energy, whether it's matter, whether it's space-time energy, that I'm labeling here by rho, the energy density, if that accelerates in some asymmetric fashion, that will produce gravitational waves that will stream away, that we can then observe at some distance or from the source. So again, solving the Einstein equations in general is sort of impossible. That's why we need to use computers for strong field sources. But again, in the weak field, we can use linearized gravity, and that can sort of tell us, give us a good sort of intuitive feel for how to produce gravitational waves through this quadrupole formula. So if we do that, then we find this. And so what it tells us, there's several things that I wanted to highlight in this expression. One, of course, if we're observing the gravitational waves distance r from the source, so we have this r over c factor, so the gravitational waves propagate at the speed of light, not a surprise. There's a 1 over r here, so the gravitational waves decrease in amplitude like 1 over the distance, which is also as expected, given the energy formula I presented on the previous page. So the energy that's going out is conserved as it expands. So this is just the dilution of energy. This quadrupole moment tensor over here, it's in a double dot, so it's a second time derivative. And so it's taking the energy density, weighting it by the coordinates and integrating. And the important thing to take away from this is what this implies is that you need an asymmetric acceleration. So a second time derivative, you need an asymmetric acceleration of matter energy to produce gravitational waves. So for example, if you have a spherically symmetric source like a pulsating star, it doesn't produce any gravitational waves. And an oscillating mass with a dipole moment doesn't produce gravitational waves. The first, so the leading order asymmetry you need is an oscillating quadrupole moment. And for example, one example of a quadrupole moment that's most relevant here is sort of two objects orbiting each other, whether they stars or black holes. That does have a time-changing quadrupole moment, and that does produce gravitational waves. So you need an asymmetric acceleration. And then the last sort of interesting thing I want to point out about this formula is, again, here now we have in this case now it's a very small constant. So in the energy formula, it was a very large constant, but it was kind of on the other side of the equation. Now we take it over here. And again, you can see this 10 to the minus 44 seconds per kilogram per meter. This kind of also explicitly shows if we want to have some sizable metric perturbation that produces this distortion that we could measure, we need a huge acceleration of incredibly dense matter to overcome this incredibly small number. And so again, it's completely impractical to produce this I double dot that's large enough on Earth to overcome this incredibly small factor. So we have to look to sort of cataclysmic sources in the universe, like black hole collisions, which do have incredibly large time-varying quadrupole moments, and it can actually produce a gravitational wave that we might be able to see. Okay, so everything that I've described is sort of in a linearized weak field regime of general relativity. And there's actually, even before LIGO, there's been a lot of evidence that this prediction, if you will, of Einstein's theory about what space-time is like in the weak field is actually correct. And perhaps the best known example is the so-called Hulse-Taylor binary pulsar. And this is sort of observations that began, I believe it was in the 70s already. I forget now the exact date when Hulse and Taylor discovered it. But they found a pulsar, which is a spinning neutron star orbiting another star. And so they could measure the orbital period of this object. And this object is producing gravitational waves. This orbiting mass has a time-varying quadrupole moment. It's radiating gravitational waves. And at least in the weak field, you can use Newtonian gravity as a good intuition for what must happen when a system radiates gravitational waves. So Newtonian gravity says that two objects in orbit are bound, which means they have a negative binding energy, but the gravitational waves, they carry away energy. And that means that to conserve energy, the binary gets tighter, it becomes more bound, becomes more negative. So a binary system in general relativity is unstable to gravitational wave emission. As the gravitational waves are emitted, the binary becomes tighter, and eventually they're going to have to merge. But at least when they're very far apart, it's a very slow process. But what this curve essentially shows is it's feeding in both this quadrupole emission physics and the energy that it carries away. And what the little black dots are here are observations. The remarkable thing about this curve is it's not a fit to the data. It's actually the prediction of relativity. Like if you take all of this quadrupole physics formula that I've just shown you and you sort of feed it into this, you get this prediction, and it fits remarkably well. And of course, famously, Halson-Taylor got the Nobel Prize in 1993 for this observation. So this is quite strong evidence that what I've described before is actually consistent with what's happening in nature. Okay, but I've sort of been speaking about weak field. Well, that implies that general relativity actually has a strong field, which is very different from the weak field, and that actually turns out to be the case. And as you say, in general relativity, it's actually kind of surprising that the strong field regime is qualitatively different. So in Newtonian gravity, you can have strong gravitational fields, you can have weak gravitational fields, and of course, what the difference is, one is strong versus weak, but they're qualitatively the same. It's the same Newtonian force. It's minus gmm over r squared is the force between two things. One is just stronger than the other one. But in general relativity, despite there being no sort of dimension length constants in the field equations, so there's no characteristic number in Einstein gravity. It's essentially a scale invariant theory. So you might think, well, the same property should hold. There's nothing that tells you that above a certain scale or below a certain scale, you might expect something different. But there actually is a strong field regime in relativity, which is qualitatively different from the weak field. And in some sense, then the reason why it arises in relativity, despite there not being dimensional constants, is because the Einstein equations are nonlinear. And so essentially what it implies is if you're in a particular situation, say a binary system, by having two objects of a certain mass, you've introduced the scale into the problem. You've introduced, for instance, the radius of the binary or the total mass of the binary. And then relative to that scale, there can be strong versus weak field dynamics. Now, it's not easy to define what we mean by strong field gravity in general, but at least in situations where there's a concentration of energy that's kind of roughly in a spherical-like region, we have a pretty good understanding, and it's given by Kip Thorne's hoop conjecture, which I'm illustrating here. So to now imagine, so we've got this little blob of matter. It doesn't have to be spherically symmetric, but it's roughly confined in a spherical-like region, and it's got a total amount of mass m, or equivalently energy mc squared. We can think of it either way. And to understand, is this going to give us a strong field solution or a weak field solution, we apply this hoop conjecture argument. And so we take a hoop, so this radius r is a hoop that we can orientate around this mass that it completely encloses it. So it's sort of the largest sphere, the smallest sphere that completely encloses the matter. And then given those two numbers, we construct what's called the Schwarzschild radius of this object, this 2gm over c squared. And here on the left, I've illustrated an example where this matter, it's not very dense. So it's kind of a weak distribution of matter. So m is small, so the Schwarzschild radius is going to be small. And so if the Schwarzschild radius is much smaller than the radius of this hoop that encloses the object, then we're in the weak field regime. On the other end, if we sort of keep this radius fixed, this capital R, and now we increase the mass, the Schwarzschild radius is going to increase. And at some point, it's going to be larger than the mass of the object. And if that happens, then we cross over into the strong field regime of general relativity. And then the nature of space-time qualitatively changes. So what happens if you get this into the strong field regime is space-time undergoes what's called gravitational collapse. So the interior of the space-time becomes intrinsically dynamical. So all of space-time starts to flow towards some kind of a singularity. The interior becomes causally disconnected from the exterior. So an event horizon forms at the Schwarzschild radius. And then numerous interesting consequences of this. Just sort of on this third point here, I've given you one example. So, for example, if you're a stationary observer some distance outside, so for example, say over here, so you're not inside this, and you measure the rate at which your clock is running relative to some very, very distant observer, there's a time dilation, and that becomes infinite the closer the observer is to the horizon. So you start getting infinite time dilation. And so, of course, all of these things that I've kind of described here, what we simply put, it means a black hole forms. So all of these things is what we describe as a black hole. So a black hole is one of these intrinsically strong field solutions, which is very different from anything that we know from weak field gravity. It's very different from our experience of geometry or gravity in the solar system. And this is one aspect of relativity that has not, until the LIGO observations, has not had any experimental or observational sort of tests of. And that's what I'll get to as in a bit. But one thing that I also want to sort of mention a bit, so that was kind of thinking about strong field gravity, and that could just be isolated sources that are kind of sitting there that undergo collapse. Of course, when collapse happens, space-time becomes dynamical. But one thing about gravitational wave, also what I sort of mentioned about the quadrupole formula, spherically symmetric sources don't radiate. And so we can't see black holes in gravitational waves, they don't radiate. So if we want to observe gravity through gravitational waves, we have to look at dynamical sources. So for example, binaries, things that emit. So we want to ask, well, okay, how do things qualitatively change with the emission process when we approach the strong field regime? And perhaps one way to classify it, again, there's no invariant way to do that, but one way to classify it is you can say, well, that's when the quadrupole formula breaks down, which is not surprising. You've got a perturbative expansion with this little h that represents a metric perturbation, where it becomes sort of order unity, with appropriate dimensions, you'd expect it to break down. But one very interesting thing is when that happens, the luminosity, so the energy that's emitted, becomes of order the Planck luminosity. So this particular c to the fifth over g. So the strong field regime in the dynamical sector, which produces gravitational waves, so it's associated, one, with sources becoming black hole-like, but also the emission that's approaching the Planck luminosity. So if we want to sort of test that these ideas, which I've, at least the strong field regime, I've just sort of argued kind of heuristically, though they are numerical simulations of both gravitational collapse and mergers that are consistent with this. So we kind of have some idea of more concrete predictions from relativity. But the question is, does nature behave in this way? Because it's qualitatively different from the weak field, we can't just immediately rely on, say, the Hulse-Taylor binary pulsar and have it say, if that's correct, then therefore the strong field prediction should be correct, because that's a completely different set of solutions. So to sort of test this, we have to look to sources in the universe which might approach this dynamical strong field regime. And as I mentioned for the quadrupole formula, the best case is you want to go to a source which is as dense as possible. And as the densest kind of objects we think that are possible in relativity are black holes. So we want black holes involved, and we want them to be accelerating as rapidly as possible. And at least for sources in the universe that we think might exist, the ideal conditions are this binary black hole system, as I've illustrated here. So we have two black holes, they're in orbit, so they're dense concentrations of matter, and they're orbiting, they're in a binary system, they're losing gravitation, so they're losing energy to gravitational waves, so they spiral inwards. And actually, the quadrupole formula, at least when they're far apart, gives you a good estimate of the luminosity, which I've written down here. And sort of the key thing that I want to illustrate about this is that the luminosity goes like 1 over the distance to the 5th power. So it's a very nonlinear process, this so-called in-spiral. And so you can imagine that to get to this regime where there's an extremely large luminosity, you've got to get the black holes very close to each other. You want D to be very, very small, and it's naturally going to happen. So you put a binary, the two black holes in a binary, just by the emission of gravitational waves, they will evolve to that region. But then the question is, well, can can, in an astrophysical situation, we actually get to the Planck luminosity? Is that where, this quadrupole sort of physics description of a binary merger breaks down? It actually turns out that from the full numerical simulations, we know the answer is no. So with this so-called quasi-circular in-spiral that LIGO has been observing, it turns out that the maximum luminosity only reaches about 1,000th of the Planck luminosity. So from a perturbative perspective, that sounds small, but the Planck luminosity is a huge luminosity. So saying it only reaches 10 to the minus 3, it's still an incredibly large number. So 10 to the minus 3, the Planck luminosity, is actually 10 to the 23 times the luminosity of the sun. So what this is telling us that in one of these black hole mergers, that the peak luminosity, when the gravitational waves are emitting it as much as brightly as they can, they're shining as brightly in energy as 10 to the 23 suns. And so rough order of magnitude estimates, that's about as many stars as are there in the observable universe. So for a very brief instant, two black holes that merge outshine all of the visible stars in the universe combined. So it's an incredible luminosity, but in terms of getting to the strong field, it's actually not that close yet. On the other hand, the binary mergers, they do reach the strong field regime. So it's not via luminosity, but the place where the quadrupole formula actually breaks down in this in-spiral is when the two black holes get very close. So here I've sort of drawn them as pretty far apart, but you can imagine that at some point they're going to get so close that the event horizons are going to start interacting. And that's actually the point where sort of nonlinear physics shows up, and that's in the fusion of the two horizons. So if we can, and as LIGO has, if we can observe this aspect of gravity, so the merger of two black holes, so the nonlinear aspect of relativity that we're testing, the sort of key nonlinear physics is what happens when two horizons fuse into one. And that's actually something where we do need numerical simulations for. We can solve the field equations in that regime. So the key nonlinear physics that LIGO is going to tell us something about is the fusion of horizons. And that happened, it started happening in 2015. So that's when the first gravitational wave signal here, GW 150914, was observed by LIGO. This is sort of the two signals from the two detectors, the Livingston and Washington detectors in the United States. And then since then, many other systems have been observed. Here I've got this sort of famous binary neutron star merger that I'll say a little bit more about towards the end. And since then, they've probably observed close to 100 signals, most of them that are consistent with two binary black holes merging, but one and perhaps a couple of others involving neutron stars. So from 2000, Einstein's theory in 2015 was a century old, but this is the first time where we've started to get data from this dynamical strong field regime. So before sort of showing some of the quantitative, let me just show you an animation here of what this event, at least the simulations of what this event looked like in gravitational waves. So here there are the two black holes over there, the larger one and the smaller one. The parameters were chosen to mimic this first event. So a 36 solar mass black hole merging with a 29 solar mass black hole. This kind of green sort of fuzz, that's the gravitational waves that are being emitted. If you want to sort of think of this in like, what is the real scale of this thing? This is about 1,000 kilometers over there. And this animation is a lot slower than real time by about a factor of 100. So this entire event that I'm going to show you took about 40 milliseconds. And these black holes, they're orbiting each other in these late stages of the in-spiral at about 20–30% the speed of light. So they're going really fast. So of course, this is going to be slowed down by quite a lot. So let me play this. So you can see they're orbiting each other again in slow motion. But this little green fuzz is the gravitational wave that's being produced. And here it's actually very consistent with the quadrupole formula. But you can see the intensity is increasing. And that's because of this 1/d⁵ runaway effect. And so now they're getting closer and closer. It's getting brighter. And then at one instant here, they plunge together and they merge. The two horizons fuse together. And so it's that fusion process, that's then completely away from the quadrupole estimate. And one thing that perhaps that's kind of remarkable about that is how rapid it was. So a binary collision, the fusion process in relativity is incredibly inelastic. They fuse together and then settle down to a stationary black hole in an incredibly short amount of time. That's kind of so if you want, one of the predictions of nonlinear gravity for the fusion of horizons, that's an incredibly viscous process if you want. They just stick together and stop oscillating almost immediately. Okay, so that gets me to so I have a very long introduction, but I wanted to put this all in context. So what I think is perhaps the most profound highlight from everything that we've learned from gravitational waves before is this evidence for the dynamical strong field description of space-time that relativity predicts, in particular in this dynamical strong field that predicts that they're black holes. So this is really the first quantifiable scientific evidence that black holes actually exist as described by Einstein's theory. And I just want to sort of motivate this a little bit more because I think especially perhaps in the sort of in the relativity community where I am, there's Einstein's theory seems so natural. So you can say, well, why do we even doubt relativity? It's such a beautiful theory. It's got to be correct. Well, of course, one of the reasons why we want to actually test this is just basic scientific inquiry. This is how scientific theories work. A theory is not healthy if there's not experiment to back it up and vice versa. So, of course, just basic scientific inquiry. But I should mention there's actually another reason why we might want to be a little bit skeptical about the predictions of Einstein's theory in this regime where horizons exist. And that's because of the puzzle of dark energy. And as I've mentioned, that Einstein's gravity doesn't have any intrinsic scale into it. So let me just go over that argument a little bit. So to dark energy, so I'd say today there's essentially incontrovertible evidence that the observed rate of expansion of the universe is accelerating. Now, interpreting that as dark energy or a cosmological constant, if you will, comes from assuming that Einstein's theory describes the large-scale evolution of the universe, and that on large scales, on average, the universe is sort of homogeneous and isotropic, and it's given by the so-called Friedman, Robertson, Lemaitre, Walker metrics. And so if you assume that you plug it into general relativity, you get the Friedman equations, and then you match what the Friedman equations predict with what's observed about the expansion rate. And if you don't include dark energy, it's essentially completely wrong. It misses the expansion completely, and you can fix it by adding dark energy. So the notion that the reason why we think dark energies exist comes essentially from assuming that Einstein's gravity is correct on large scales, and therefore there has to be something else, some kind of matter that we're missing. But what I want to point out is that on the scales of the Hubble radius, so the size of the universe, we're always in the dynamical strong field regime as I've sort of defined it before. And so that the kind of physics that describes the fusions of horizons is in some sense very similar to the physics of the universe on large scales. So not just at the Big Bang, but even today on large scales, the universe is in the dynamical strong field regime. And just to argue that, we can actually just go to the hoop conjecture again. So for example, if we take, let's take a bit of energy rho here, and let's just now imagine for a second that we're not in a Friedman-Robertson-Walker space, but in an asymptotically flat space, like so that there's a radius and there's an infinite space outside. Now let's fill up a sphere of radius r with just constant dust, if you will, just energy rho here. So this is the mass, the volume times the radius. We can compute its Schwarzschild radius here, and then we can say, well, as we add energy density, at some point the Schwarzschild radius is going to grow. At some point the Schwarzschild radius is going to equal that, and we can ask, well, when does it happen? It happens when this. Just solve this equation. So this is the hoop conjecture for what size of object of a constant density do we expect a black hole to form. And so now we can ask, well, let's make rho the average density of material in the universe today, which is an incredibly small number, 10 to the minus 20 something, I forget, kilograms per cubic meter. So the average density of matter in the universe. So that's the interesting thing here. Black holes, the strong field regime you don't necessarily reach it with high densities. It's this criteria. It doesn't necessarily mean high or low density. So you get incredibly low density material, but if you just have enough of it, you will get to the strong field regime. Now, if we go to the Friedman equation, and we say, well, what does it tell us about the universe? So it's sort of one way to sort of roughly estimate the size of the universe is the so-called Hubble radius. So it's the speed of light divided by the Hubble parameter, which is the fractional change in expansion as a function of time. And if you sort of plug that into the Friedman equations, this is what the Friedman equations tell you. And then if this is the rough radius of the universe, it actually tells you that the radius of the universe at any epoch is exactly this Schwarzschild radius that I've sort of estimated with this formula. Okay, so the thing is, like, don't panic. We're not inside a black hole. The reason why we can get these two qualitatively very different solutions, so this Friedman-Robertson-Walker expanding cosmology, or a space-time about to collapse into a black hole, is because the Einstein equations are nonlinear. They allow these two different topologies of solutions, if you will. But the point about this is not to argue that we're inside a black hole or not. It's really to illustrate that on scales of the Hubble radius, we are in the strong field regime of relativity. So I think getting some evidence that we understand this, or that nature is really telling us that Einstein theory tells us how geometry behaves in such a regime, I think is important, not just only for black holes, but it could help with sort of, getting more evidence that we should take dark energy seriously. On the other hand, I should also mention one caveat is that there are many possible explanations or ideas that people have come up with that would explain dark energy. Some of them involve modified gravity, modified relativity, and many of these modifications do introduce a scale which change things on universe-size scales versus astrophysical black hole scales. So you can definitely avoid this kind of general relativity scale invariant notion of gravity with modified gravity. But I think it's still an interesting connection here that if we want to, it's very useful to know if relativity is, if the predictions in this nonlinear regime is consistent with what's going on in nature. Okay, so you also might want to ask, well, haven't we had evidence for black holes for a very long time? And yes, the evidence for black holes has steadily grown over the years. From the 70s, through the 90s, 2000s, the orbit has been stellar mass black hole. In fact, the Nobel Prize was given last year to Ghez and Genzel for discovering this ultra compact object in the center of our galaxy. However, all of this, the evidence that's been growing has really been that the universe does have dense, dark, ultra compact objects. But none of this evidence here actually pointed to Kerr black holes as governed by relativity. So all of this, if you will, was circumstantial evidence that black holes existed, in the sense that these dark ultra compact objects exist. It's difficult to explain them if they weren't black holes, but there isn't any independent information that they actually are Kerr black holes as governed by relativity. So that's why the LIGO observations are sort of different in this regard, because it's actually giving us some direct evidence that space-time, at least in this merger regime, is as governed by relativity. And so also just this figure, I also like to one aspect about the LIGO data, which is interesting, just to emphasize like how much of the data is actually coming from this merger regime. So here is so this green curve here. This is from a numerical relativity simulation of the event. So here, this is kind of, if you will, quadrupole formula in spiral, and this is the merger, and this is the ring down. But what this little cyan curve over there is saying, well, okay, what if you take this signal and feed it through LIGO's sort of observational pipeline? So the thing with LIGO is it's the detectors have a frequency dependent sensitivity. So it doesn't have it doesn't see all of these frequencies with the same strength. And this is actually what it would see if you filtered it through the noise curve. So unfortunately, it's not very sensitive to these low frequencies, so you don't see anything, but it's sort of perfectly at least with this first event, sensitive to just the merger ring-down regime. So LIGO, with these kind of heavier black holes, kind of are sort of perfect observatories to look into this dynamical strong field regime where two horizons merge. So we're actually getting some kind of exquisite data about the merger of black holes. So let me just give you one example. So I am sort of getting towards the end of time, so I'm not going to sort of focus on this much. I just want to also briefly mention some of the other things. So let me just say, so there are many ways in which we can sort of quantitatively test that is this consistent with relativity. One is just to say, well, does the numerical signal after we filter it through the data, is it consistent with this full signal? And it is. But another perhaps way that's kind of interesting to quantify the consistency is to make use of the so-called uniqueness properties of black holes. So black holes in general relativity are predicted to be very simple objects, at least parametrically. So if you know the mass and the spin of the black hole, you know it's full space-time, the so-called no-hair theorems. So that implies that this full merger waveform is actually only described by a very small set of parameters, the mass and the spin of the two black holes, the initial orbit, and that's about it. And so what that means is that there's actually more information in the signal than there really is sort of that we need to characterize the system from the fundamental physical theory, relativity. So for example, then what LIGO could do is they can take this early in spiral, they can estimate the mass and the spin of the two black holes, they feed that into a numerical simulation, if you will, that then predicts what the final mass and the spin is to come up with a prediction for the final mass and the spin. The other thing that they can do is they can measure this decay, this ring down as it settles down to a quiescent black hole. And then perturbation theory tells us that the decay, the frequency and decay of this ring down signal also is uniquely a function of the final mass and spin. And so you can then invert that and also get an independent estimate of the final mass and spin. So to recap, so from just this in spiral, you can predict what the final mass and spin is. And just from this ring down, you can also then get an estimate of the mass and spin. And of course, if this is relativity, they better be consistent. And that's what this figure here shows. So this is from the LIGO collaboration from the most recent data. And this is taking these two different estimates here on the horizontal axis. That's the difference in these two mass measurements. So if they're consistent, they should be around 0. And a difference in the spin measurements, and if they're consistent, that should be around 0. And essentially, it's normalized in some sense that this entire box is everything that's allowed by relativity. So it's sort of normalized that this is all the possibilities. And each one of these contours is from a given individual event. So you can see that each individual event doesn't give a very strong constraint yet. They're not that high signal to noise yet. But at least if you combine them statistically as a population, it's now starting to become a pretty tight constraint that this is consistent with the predictions of relativity. Okay, so now, in the last 10 minutes, let me very, very quickly go through these last set of highlights. And this is not that they are less significant. I just for the sake of time, I decided to focus on, what for me is the most exciting thing is, this giving us evidence for the existence of black holes and that their dynamics is described by relativity. So these, I'd suggest if you haven't had the talks about the binary neutron star, this could be a whole talk, and I'd suggest you invite an expert on that to talk about it. So I'm just going to very quickly go through a couple of the highlights from this. So the second, I think, profound discovery that they made was in 2017, they observed the merger of two neutron stars that then collided and produced a host of other electromagnetic signals that were also detected. So here on the gravitational wave side, you see this is the in spiral. In fact, this is actually quadrupole physics as well. You can sort of that line there that you can get directly from quadrupole physics. So this is the gravitational wave emission seen by the three observatories. And then remarkably, it was sort of within a couple of seconds of the end of this, the Fermi satellite saw a short gamma ray burst that was in the same region of the sky. Within about a half a day afterwards, optical telescope surveys that then try to find this event in the sky actually found the event in a galaxy about 40 megaparsecs away. So that's what that dot shows. So this combination of being able to see it in gravitational waves and also the counterpart emission, well, that told us that it was a binary neutron star merger. So this signal by itself, it's very difficult to differentiate between a black hole and a neutron star. But the fact that so when the neutron stars collided, it was a tremendous explosion. The aftermath was then seen in electromagnetic waves. So what did we learn from that? Well, numerous things. Well, the first thing was that this gave us an actual test of, I mentioned gravitational waves travel at the speed of light. That's a prediction of Einstein's theory. But this was sort of the first bit of evidence that that is correct. And it tells us that gravitational waves propagate at the speed of light to within 1 part in 10 to the 15. So that's coming from the fact that the gamma ray burst, which was assumed to be produced when they collided, was observed within 2 seconds of the gravitational wave signal ending there. And then because this event is so far, it came to such an exquisitely precise measurement of the speed of gravitational waves. This also then, because the gamma ray burst was observed coincident with this told us that at least some class of short gamma ray bursts are produced by neutron stars, which up until this point, that was a mystery. It was theorized that was possible, but this was the first evidence that told us that's the case. What produced the optical afterglow of this explosion that lasted, it peaked within a few days or a week or so of this was, as the neutron stars collided, a lot of material was tidally stripped from the system. So there was this neutron-rich material that was stripped off, and as it sort of expanded, it underwent this so-called R process that produced very heavy elements like gold, platinum, uranium, etc. But also produced a lot of elements that are unstable to radioactive decay. And then they started radioactively decaying into lighter elements. And it's the radioactive decay of those that produced the so-called kilonova, in analogy with a supernova, which is also produced by radioactive decay. I think of nickel. So this kilonova was also predicted to come from neutron stars, so it was observed. And one little interesting fact, you probably all sort of heard of this, is if you take this one event, try to estimate, well, how frequently do neutron star mergers occur, and how much of the heavy elements were ejected into space by this, it actually turns out that binary neutron star mergers can, in principle, account for all the universe's abundance of heavy elements, such as gold and platinum. So there's all this bling that humans like to adorn ourselves with, that most likely it's the ashes of the remnants of binary neutron star mergers. That's where it comes from. So that's kind of an interesting fact. Another thing, which let me just mention this in words, just again for the sake of time. Let me not go into this in detail, but what it came from, another thing that you can do with binary neutron stars is it's a so-called standard siren, where you can actually measure the cosmic expansion in a way that bypasses the cosmological distance ladder. So you don't have to calibrate the intrinsic luminosity of the source, because you get the prediction from the quadrupole formula. Essentially, that tells you what the luminosity of the source is. So if you know what the luminosity is, which LIGO measures, and you can find a counterpart, which the optical telescopes did, you get a redshift. And so you can get a redshift luminosity distance measure that bypasses the so-called cosmological distance ladder. And this gives you a measure of the local expansion rate of the universe, which is independent from these other parameters. And as many of you probably know, there's right now an interesting so-called tension in the estimate that's derived from measurements of the cosmic microwave background with this Planck satellite versus local supernova. Here's one example from the SHOES observations. So this orange versus, I guess, greenish line here are the two different observations, and you can see that they're not consistent with one another. Now, this is this first LIGO observation. Now, the error bars are too large to help resolve this tension, but the hope is that over the next few years, as more objects are observed, this tension will be reduced. Just very quickly, so I mentioned that without a counterpart, it's very difficult for LIGO Virgo to tell the difference between black holes and neutron stars. But one, in principle, with a very high signal to noise ratio event, if the high frequency part of the signal is you can start noticing a difference because the neutron stars are tidally deformed. But that really only happens very close to the end, which LIGO loses sensitivity at the high frequencies. But still, there's a little bit of an imprint of the tidal deformability in the signal. And that's what this diagram is illustrating. So they actually did measure some evidence, just purely from the gravitational waves that these weren't black holes. So this is an estimate of the tidal deformability. If it was black holes, it should be peaked around 0. But you can see that the peak has kind of shifted to a deformation. It doesn't rule out 0 statistically, but there is some evidence for it just purely from the gravitational waves. And the interesting thing about these tidal deformability measurements is it can tell you something about the equation of state of matter at these nuclear densities, which is also unknown at this point. And this is also one of the big promises of observing binary neutron stars with gravitational waves going forward, is to measure the equation of state. Now, the final sort of set of highlights are some unusual properties of stellar mass black holes. Yes, my apologies for rushing. I see we're sort of getting to the end of time, so I'll just very, very quickly go over these. And this is sort of a diagram that represents essentially all of the mergers that LIGO has seen. So the vertical axis is the mass of the compact objects here. The blue ones are the black holes that LIGO has seen. The horizontal axis is just spreading it out. It doesn't have any scale. It's just to separate them. And so you can see for the mergers, each one of these consists of 3 objects. So it's, for instance, 2 black holes of these masses merging into one. What's also shown on this figure are candidate black holes that we see in our galaxy from electromagnetic observation. So these are candidate black holes in stellar X-ray stellar binaries, these red ones. And these are observed pulsars, for instance, neutron stars in our galaxy. So the first thing that's unusual about the black holes that LIGO has seen is that most of them are much more massive than the known black holes in our galaxy. And so the question is there something significant? Is there an interesting reason for that? Or could it just be a selection effect? Or are there different classes of black hole, or there are different populations of black holes that arise? And we don't know, but this is one of the sort of an interesting, unusual thing about these current observations. Another interesting thing that LIGO has noticed is that most of the black holes that they observe before they merge, so these the 2 little ones that eventually become the 3rd one, is that the 2 black holes, the progenitors, aren't spinning very rapidly in most of the cases. The final black hole, the merged object, is spinning quite rapidly, but the progenitors aren't spinning very rapidly. And the question is that telling us something interesting? Or is it just the mundane explanations is that these black holes were born from stellar collapse, a billion years before they merged? It might just be that black holes are born with low spin. But there are some other possibilities. One is that these ultralight sort of axion-like particles exist that actually spin down black holes after they're born. So that's sort of an exotic possibility. People have also suggested that these actually might be primordial black holes, the ones with low spin, because scenarios of black holes being formed not from stellar collapse, but very early in the universe, the so-called primordial black holes, might also not be born with low spin. So we don't know yet. This is also something that will hopefully become clearer with more observations, but this is kind of an interesting thing that progenitors have been observed to have low spin. And then the last point is that there are a couple of objects where the black holes have unusual masses. Also, the compact objects, in this case, have unusual masses in the so-called mass gap. So in stellar evolution theory, suggests that it's difficult to form black holes between 2.5 and 5 solar masses. And here's an object which they observed that was 2.6 solar masses, but there's an error bar, so it might not exactly be in the mass gap. But if this really were a black hole, that would be interesting. If this were actually a neutron star, that would be also be interesting. It's kind of challenging to get neutron stars that massive. So this is an interesting object from that perspective. And there have been a couple of mergers where the black holes have been quite heavy in a different kind of a mass gap. So again, stellar evolution theory says that stars that would form black holes in this range, and these numbers are kind of uncertain, but 65 to 135 times the mass of the sun, suffer the so-called pulsational pair instability before they can form black holes. And when this instability sets in, it blows the star apart. So theory says that we shouldn't see black holes in this range. And these objects, again, the error bars are large, so they might not exactly be in the mass gap, but they're kind of some interesting things. And again, more confirmation will come in the years to come as more events are observed. So sorry for rushing over some of those other highlights, but let me then just conclude with just some comments about what I think, where are we going to go in the next decade or two? And that's going to come from a combination of improvements to the ground-based detector, their sensitivity, the LIGO Virgo detectors. A detector in Japan is coming online, the Kagra detector. LIGO is going to be building one in India. So there's going to be a large network of detectors in the 5 to 10 year range that should, so everything that I've discussed, tests of relativity, understanding the populations of objects, measurements of the Hubble constant, etc., all of these things we can expect factors of 2 to 3 improvement. Now, hopefully, people are also planning this next generation of ground-based detectors, the Einstein telescope, the Cosmic Explorer that might be built in the 2030s. And if that's the case, they should include sort of an order of magnitude, a factor of 10 improvement in some of these quantities. You would say, okay, what's an order of magnitude? Well, in some cases, it could be very significant. So for example, this first black hole merger that was discovered was at 400 megaparsecs from us. Now, if we estimate what's the size of the observable universe, through this, the Hubble constant estimate, it's about 4 gigaparsecs. So this was about a 10th to the edge of the observable universe. So if you can increase the sensitivity by a factor of 10, remember the 1 over R decay of gravitational waves, this implies that the third generation detectors will be able to see such kind of black hole mergers throughout the visible universe, which is pretty remarkable. So a factor of 10 could be incredibly significant. And I'll just finish by also mentioning this. There are actually other campaigns to observe gravitational waves that didn't focus on cosmic microwave backgrounds and pulsar timing. They haven't yet detected anything. They've placed limits on it, but I think it's quite likely that within the next few years, both pulsar timing and probably cosmic microwave observations, well, pulsar timing, I think definitely will detect some stochastic background. Pulsar timing the CMB will either detect something or place very stringent constraints on the large scale cosmic background, which would be interesting as well. Okay, so thank you for your time. I apologize for going a little bit over, but thank you.
No, Frans, nothing to apologize. Thank you very much for an excellent and very, very, very interesting talk. During your talk, I asked Yingxue, since he joined us, if he would kindly guide us through the Q&A session. Yingxue, over to you.
Yeah. Okay, thank you. Yeah, masterpiece. It's a wonderful talk. Thank you very much. Yeah,
thank you.
And yeah, so I see that in the Q&A and also the chat window, there are a number of questions. Okay, let me just, I mean, we may not have time to go through them all, but I mean, there's a few interesting. There's one question said, as much as singularity are a natural consequence of the theory in general relativity, could they truly exist in reality? Would not their existence imply an infinite geometric space-time?
Yeah, that's a good question. I think so. What I'd say the predominant perspective on singularities in general relativity, right? So general relativity is unambiguous. Once gravitational collapse happens, there is some kind of singularity. We don't exactly know generically what it is. Is it a curvature singularity? Is it some kind of an incompleteness in space-time? But there is definitely something that goes wrong. And I would say that most people, the philosophical resolution to this is that Einstein's theory is actually becoming invalid there, that it's breaking down. So you might think that in analogy, it's like in fluid mechanics, there are also singularities that occur, for instance, when shock waves form, etc. But we know that, say, for instance, when a shock wave form, there are no infinities that are showing up there. If you zoom in sufficiently, closely, you'll see that they're actually molecules and atoms, and that resolves the singularity. So the usual, I would say that the predominant idea is that Einstein's gravity is sort of telling us that there are regimes where it fails to be the actual theory. We don't know what that theory is. People think it's a quantum gravity. Let's just say quantum gravity for lack of a better idea. And I mean, there are good arguments for why it should be a quantum theory of gravity. But yeah, so definitely I'd say singularities are a problem if we wanted to take them seriously. And so most of us say we don't take them seriously, except insofar as the theory is telling us we need a better theory. Now, if the so-called cosmic censorship idea of Penrose bears out, and this is saying that yes, singularities do occur, but they're always hidden behind event horizons. In some sense, that's you can think of that conjecture, and it seems to hold out in most situations in relativity, is both a good thing and a bad thing. So it's a good thing in the sense that it allows us to predict what happens when black holes merge, for instance. Because even though there are singularities inside the black holes, that doesn't allow us to predict what happens inside black holes, because of this event horizon property, it's not going to influence our predictions from outside. So we can actually get a concrete prediction of everything that happens outside the black hole mergers. So it's kind of a nice conjecture for our ability to understand gravity outside. But on the other hand, like why would, say, quantum gravity care about being censored? So on the other hand, cosmic censorship is saying it doesn't allow us to see how quantum gravity resolves a singularity, which is unfortunate. It would actually be great if there were some scenario out in the universe which did form a so-called naked singularity, and we could actually see what quantum gravity does, or whatever theory comes beyond Einstein gravity, whatever theory that is. But unfortunately, it seems that for these astrophysical mergers, they're all censored. Sorry, a very, very long-winded answer to that question.
May I just follow up on his question? I mean, you were famous on developing the early numerical code to simulate black hole merger, etc. I mean, certainly in your code, you have to identify a black hole at some point. And how can you identify an infinity, or how do you deal with that?
Yeah, so it's a good question. So the thing is, so assume that cosmic censorship held. And so in some sense, if cosmic censorship failed, it would have been almost a proof by contradiction in the following sense. So we have these two black holes. We assume cosmic censorship. So actually in the simulations, we cut out the interiors of the black hole, something called excision. So we excise the interiors. So we only simulate the space-time up until the horizon and a little bit inside the horizon. So we know, yes, there are singularities inside, but we got rid of them. And yeah, until we could simulate the merger, we didn't know if that was self-consistent. So if a merger produced a naked singularity, what would have happened is, so we assume that they're not naked. At some point, a singularity shows up, the code would have crashed. Because yeah, we cannot deal with infinities. And so it was something we didn't know if we could actually, if we could actually go all the way through a merger without this happening. But then eventually, when we started to actually simulate these mergers, we found that the horizons fused in a way where the interior was always excised and no singularities showed up outside. So it's a situation where, yeah, we can deal with singularities, we can simulate them. We have to assume that they're not there. And if a scenario forms where it would have been naked, the code would have crashed and we would have lost predictability. So again, lucky for being able to predict it, but sort of unlucky for being able to learn about, quantum gravity, if you will.
Yeah. Thank you. Yeah, fantastic. And there's another question which I find interesting. Are there any limitations to Thorne's hoop conjecture, i.e., is it restricted to classical 4D universes?
Well, that's a good question. So it is a bit of a heuristic conjecture. And actually, I should say that the original way in which Thorne sort of came up with it was actually not in the way that I presented it. So he actually was in a situation where saying, let's assume gravitational collapse is happening. So we're now in this nonlinear regime. And he said, he was actually trying to address this cosmic censorship issue. So when do naked singularities form versus event horizons? And he conjectured that if the collapse happens in such a way where you can't have this hoop surrounding it. So let's say it was a very elongated situation, like a cigar-shaped object collapsing, then a naked singularity would form. And so he said, well, okay, if this hoop can surround it everywhere, then an event horizon would form. But since then, the way that I've presented it, I've kind of modified the conjecture just to sort of say, okay, let's assume cosmic censorship should be satisfied. We don't have an elongated thing. We just have the spherical-like collapse that tells us when a black hole would form or not. But in some sense, it's kind of heuristic, and there are a few examples that shows that it's fine in 4 dimensions. If you go into higher dimensions, I think there are a couple of examples where it does work as well. But I wouldn't be surprised if you could find counterexamples. Like I don't think it's a very generic. It's not generic in the sense of independent of dimensions. And actually, also, if you go beyond 4 dimensions, there are definitely examples where Einstein gravity does produce naked singularity. So cosmic censorship is not respected in higher dimensions. So, for example, one famous example is the Gregory-Laflamme instability of black strings. So, like higher dimensional black strings, they fragment into little black holes, and when they do, they produce naked singularity. So I think you can apply loop conjecture type arguments in higher dimensions, but there are going to be lots of caveats and there will be exceptions, and cosmic censorship isn't respected outside of 4 dimensions.
Thank you. I just want to check with the chair, Francesco, do we have more time or should we?
Yingxue, I think we might have maybe 5 minutes, because I know that Frans needs to leave just now for another commitment. So maybe you can pick let's say 2 more interesting questions.
Okay, so then I would take this advantage to ask a question of myself. So in 2017, we had a lot of discussion in Perimeter Institute on the echo after the merger. There was this nonlinear event, and the people calculate the significance of the echo after that, and there was a lot of debate. I mean, it was some people calculate about 2 sigma, etc. And what is there any follow up of that, and what is significant of this?
Yeah. So just to put in context for people that don't know about echoes. So in general relativity, there's no echo. So the black holes merge and they ring down and the signal ends. But then people have suggested, well, what if actually these aren't black holes, but these are some ultra compact objects that don't have horizons? So that's a good question to pose. And so if they're ultra compact objects that don't have horizons, it might produce some kind of a ring down, but then the gravitational waves are sort of propagating around, and there could be echoes of the ring down that show up. And again, there were some indications by some groups that there actually might be some, there might be some indications of echoes in the signal. But at least I'm not an expert on all the data analysis, but so LIGO reinvestigated their data, and they've also now in their more recent analysis of the larger class of objects, and they claim that they don't see any echoes in the signal. So, that doesn't rule out these echo objects, because the thing is, so LIGO is now just starting to see these mergers. There were a couple of events, like the first one where the ring down has a signal to noise, just the ring down piece of around 7 to 8. So it's enough for a definite detection. You can measure the decay, but the echoes are expected to be a lot dimmer. So the fact that for these events, if these actually aren't black holes and they are echoing, we'd need a much louder event or a much larger population to actually rule them out. So right now, there's no evidence that there are echoes. In my opinion, of sort of looking at what people have published and what LIGO has published, I'd say there's no evidence for echoes, but it's too early to rule them out.
Oh, thank you very much. Thank you for your answer. Yeah. Oh, Francesco.
Thank you. Then Yingxue, let me follow your example and ask my question myself. Just a very probably stupid question, Frans. Would it make sense for South Africa to aim of building a LIGO detector? Because are there any in the Southern Hemisphere?
No, yeah, actually, I'd say yes. The problem, of course, is budget, and I don't.
No. Budget is just a number, yeah. But from the science point of view, would it make sense or not?
Yeah, so the one thing, having more detectors, well, what it helps in eliminating noise sources, so false alarms. But I think once you have, let's just say we go to very loud events where there's, if 2 detectors detect them, that's fine. But what having multiple detectors has is it improves the sky coverage. So the LIGO detectors, they've got a pretty broad sky coverage, but there are certain blind spots. So if you have different orientations for the detectors, you'll cover the different blind spots. And then also the more detectors you have, so okay, one way to cover blind spots is have detectors at different orientations, but if they're at the same place on the planet, that would help you with localization. Because one way in which they localize it, or the main way in which they localize it, is just different times at which the signals arrive at the detectors. So now with Virgo, that's helping, but having one in the southern hemisphere will improve significantly with localization.
Okay. Let's start lobbying.
Yeah.
No, because we have in the Karoo, we have an astronomically protected area, yeah. And so there is already a whole infrastructure. Maybe it would make sense to exploit it maximally. Yeah.
Yeah, definitely. I think that would be great.
Okay. Then we will try to set up a budget with Yingxia.
Yeah.
Okay.
A few doors. Yeah.
Yes.
Okay. Then thank you very much, Frans. It was really, as Yingxia said, a wonderful talk. And we are very, very grateful that you took the time to be with us out of probably very, very hectic schedule in your part of the world. Then thank you very much. Let's hope that in the not too distant future, we can invite you again to tell us the rest of the story, how this very fascinating part of physics evolves. And we wish you...
Hopefully in person.
Yeah, and maybe we can start to build a LIGO in the Karoo. Yeah, Yingxia and me will go there and start pulling a few, strings. Yeah. No, thank you very much. Then we wish you a nice rest of the day. And all other participants, thank you very much, and a good evening, and all the best for your Valentine's dinners. Yeah, because that's
thank you very much.
Be on your agenda as well. Yeah, and to you as well, Frans, of course. Thank you.
Thanks, and I hope everyone enjoyed the talk, and thank you all for your time. And,
yeah, no, definitely.
I enjoyed it very much.
It was wonderful. Thank you very much. Thank you. Have a good evening, everyone, and a good day to you. Yeah, bye.
Yeah, thank you.
Thank you, Ilya. Thank you very much. Bye.